I'm Amitafa Michael, a member of Group 6, and I'll be talking about the introduction of this project. So, this project presents a tax settling system designed to manage and process tax efficiently based on priority and time constraints. This system is useful for students, software developers, and project managers who need to organize tax and manage work effectively. Beyond the basic three syllabus requirements, we extended our system with several advanced features. We built an interactive Tinta graphical user interface for easy user interaction. In addition, we introduced a staging area for temporary tax handling before execution and applied the observer pattern to enable automatic system updates. So these features demonstrate a more practical and efficient settling tax system beyond the basic syllabus.
Good day. I'm Banamkuru Mary Vanessa, and I'll be taking you through the layout and the key interface features of the tax scheduler application. On the left, we have the sidebar, which shows the tax statistics like the pending, completed, overdue tax, and also the stage tax. Alongside that, we also have the priority guide. It tells users the agency level of their tax. In the center, there's a tree view table that displays all tax with details such as priority, tax name, deadline, and then the status. The tax are automatically sorted by agency. On the right, we have the input forms where users can create or update tax by entering details like their names and their descriptions, the deadline, and also the priority. Above the table is the action bar, which includes controls like the run next tax, the pick next, the run selected, remove, and admit states, allowing users to manage tax efficiently. Pick next shows the highest priority task without executing it, while the run selected allows users to override the queue and run any selected text immediately.
I'm Daniel Kuma JB. Alright, so over here is the add new tax section. Basically, this is where you enter your tax name and then maybe add a description and set a deadline if you want. It's pretty straightforward and quick to use. Okay, so now one thing I like here is the priority slider. Yeah, instead of typing anything, you just drag it from 1 to 5, and each level represents how important the tax is. That's from critical down to background over there. And as you move it, you can see the color and then the label change instantly, which makes it really easy to understand. Once you are done, you got two options. You can add the text directly and also the queue, or you can use the batching feature, which has been implemented over there. So with batching, you can click stage and then the text doesn't go straight into the system. It's just held temporarily. Then you are ready. You hit the stage only if you are ready, and all those stage stars get pushed into the live heap at once, where they are sorted by priority.
Good day, everyone. Now I'll walk you through how we handled our tax priority updates in our system. First, we have the change priority form, which allows users to select an existing tax and assign it a new priority value. This makes the system flexible since the priority can change dynamically based on the user's needs. Once a new priority is selected, clicking the apply button immediately updates the system. Behind the scenes, the tax is reinserted into the heaps and the entire structure is reheapified. This ensures that the tax list is always correctly sorted based on the priority, with the highest priority at the top. Finally, we have the execution history table. This logs all completed tasks, including important details like their execution time and how long they have waited before being processed. This feature helps users track performance and give insights into how efficient tasks are being handled.
Hello, I'm Akusia Kunido Favia, and I'll continue from here. So, one of the most advanced parts of our Scala is its background automation. Rather than waiting for the user to manually adjust tasks, our system continuously monitors and manages the tasks behind the scenes. The first automation feature is the priority agent. In traditional priority queues, low priority tasks can suffer from starvation, meaning they can never get executed if high priority tasks keep arriving. To solve this, our scalar tracks how long each task has been waiting in line using an age task counter. So after a specific number of cycles, the task priority is automatically increased. This guarantees that every task eventually rises in urgency. Our second feature is the deadline enforcement. The scheduler constantly checks each task deadline against the current time. If a task becomes overdue, its priority is immediately escalated to critical, pushing it to the top of the heap for urgent attention. At the same time, our live analytics sidebar updates automatically.
I'm Kwame Adom Asuma Peprem, and I'll be walking you through the core data structures and the staging logic behind the scheduler. So everything starts with our task class over here, and then every task that is born into the system gets created at timestamp. So we have also an age ticks counter that quietly tracks how long it's been sitting in the queue. We also overloaded the less than operator so that Python can compare the two tasks by urgency naturally. And this is an implementation of polymorphism. And from here, we have tasks that enter the custom minimum heap where we have a binary tree living inside a plain array. So every parent node is found at an index I minus 1 or divided by 2. So no built-in libraries, everything is written from scratch. And then before anything hits the heap, it will pass through our task queue, which is a strict first in, first out staging area that holds batch tasks until they are ready to be admitted all at once.
Now let's sift down. Now, even we have our priority queue and we move the route, we have to take something to replace it. So we take the last element to place it in the root. Now, to maintain the heaping property, what element that we've exactly placed into the root may not be the one with the highest priority. So we use a sift down to shift it into position to ensure that the heaping property is maintained. And to prevent the CPU from overloading because of a multitude of multiple tasks, we use the first in first out principle, which is an algorithm we use to ensure that the CPU is not overloaded, where the first task that comes in is doing to the first one that comes out. By doing this, we ensure that the time complexity is always off and the CPU is not overloaded.
In our GUI architecture, we applied inheritance by allowing the app class to inherit from Tinker, which helps us reuse built-in GUI features like windows, buttons, and event handling instead of creating everything from scratch. From there, we move to the core engine, which is the task scheduler, the heart of the system. It manages how tasks are added either directly with our tasks or placed in a rating queue using state tasks before being admitted in batches. Finally, the execute next method uses a greedy algorithm by always selecting the highest priority task first from the heap. This improves efficiency while also tracking important details like waiting times and whether deadlines are met.
My name is Christopher Boateng, and I'm here to take you through the core principles of our project. Now, since our schedule runs on time-critical loops, we couldn't let the backend computation block the UI thread. So we designed an event-driven bridge instead of direct cells to prevent what UI freezing. Now, for the observer pub sub pattern, we applied the observer pub pattern engine, which publishes state changes like priority escalations or deadline triggers are sliced with events, not method calls. And for the last part, which is the decoupling stage, the GUI registers interest via subscribe, event type, and callback. When the engine notifies the event, it pushes only the minimal states delta. No pulling, no type coupling, just clean, asynchronous updates that keep the UI responsive. Thank you.
Hello, my name is Oliver Larikok, and I'll be wrapping up our presentation and highlighting how our system interacts with the user. So, in our system, we implemented a toast function with a timed callback. The reason we use the toast function is because we wanted to make the overall system more responsive, more reactive, and more user-friendly. So, with using the toast function, whenever a user performs an action like removing, updating, or adding a task to the task scheduler, a floating message appears in the screen telling the user about which action has been performed. And that is by use of the toast function. And then in the future, we plan on integrating a database so that more information or data can be stored permanently even when the application is closed. Overall, the goal of our system is to combine task scheduling with real-time user interaction. Thank you.